In the last video, we talked about the basic theory of quantization, such as linear quantization. I have a blog post related to that as well. You can go through it. In this video, we'll talk about the theory and implementation behind some of the popular libraries in quantization, such as GPTQ, AWQ, and GGUF. Hi, my name is Joydeep. I am a senior machine learning researcher and have 14 years of experience. In this channel, we talk about AI from basics. Since there are a lot of quantization papers, we are only going through the important ones, which are in Hugging Face, somewhat new and somewhat in use. We will start with linear quantization and how to do linear quantization using Optimum-Quanto. We have discussed about Optimum-Quanto in the previous video as well. This is a fairly new library with release in October 2023. The other libraries will check out chronologically because this is the simplest method as we have seen and wanted to cover it first. So here you can see you pass the model ID, so something like MetaLlama 3 billion instruct. You load the tokenizer, and in the model, the tokenizer and the model you load as you would load generally. Then to quantize the model, you pull quantize and the quantization type, and then you perform the quantization. Next, we'll start with BitsandBytes. This paper came out in June 2022. It started out with the research regarding quantization at Hugging Face and its FP8 implementation. The research was primarily done by Tim Detmers, who is a big name in the quantization community. In the last 10 odd years, he has done a lot of research with big names like Intent Quantization and QLoRa. In the LLM Intent paper, they basically studied the effect of outliers in the transformers and did mixed precision decomposition for better output. They implemented this using blockwise quantization, which we have also seen in the previous video, so I'll not go into deep into it. This is for the 8-bit quantization. For moving to 4-bit quantization, QLoRa was introduced in BitsandBytes. Let's look at the 8-bit code. If you load the MetaLlama 3 8 billion instruct model, then the memory usage is around 13 GB. So before going ahead, let me just take you into some of the common code that I have written. So we are loading, we are doing the Hugging Face login here. So one thing we'll try to do is calculate the perplexity for this of the models. For this, I am loading the Sumeru code text Python dataset and just loading 100 samples from it. You can take more samples or create your own dataset for your use case. This is the code of calculating the perplexity, where we take the outputs from the models and then check the negative log likelihood of the loss and compare it with the actual tokens. Then we average the negative log likelihood per token. So this is the perplexity for the specific model. We also check the GPU utilization using this code. So we have just seen that loading the base model takes around 13 GB. If we calculate the perplexity, we have perplexity of 5.28, and total for 100 samples for 100 data, it takes around 11 minutes. We can compare this to the 8-bit model quantized using BitsandBytes. For this, we have to create the quantization config. So in the quantization config, load in 8-bit is true. This will create the quantized model. Once loaded, you can see the model now is taking 8 GB of memory. So we can run the we can check the GPU memory utilization and calculate the perplexity. Right now, perplexity for the quantized model is 5.32. So this graph shows the comparison between the unquantized and the quantized model. So you get huge gains in memory and time without much or rather without almost no loss in perplexity. Now let's talk about the GPTQ algorithm. This algorithm was submitted in 31 October 2022. GPTQ is a post-training quantization method to make the model smaller with a calibration dataset. For every layer L in the network, we want to find a quantized version W hat of the original weights W. This is called the layer-wise compression problem. Concretely, if W is the weights of the linear layer and X is the input corresponding to a small set of m data points running through the network. Then the objective is to find a matrix of quantized weights W which minimizes the squared error relative to the full precision layer output. Hence we can say that as argmin of W hat. So for the quantized weights, take the squared error of the outputs, where X is a small calibration data set of activations. So GPTQ has several key insights to make it more effective than simpler quantization approaches. First is processes weights in order of importance, focusing on the most impactful weights first. Second, it uses the Hessian metrics to understand the complex interaction between different weights. Third, it quantizes weights column by column in blocks for efficiency. And most importantly, it redistributes quantization errors to minimize their impact on model performance. Let's see what quantization actually looks like. Here are some original weights with full 32-bit precision. When we quantize them to 4-bit representation, each weight gets rounded to the nearest available value in our 4-bit representation. This introduces quantization errors, the differences between the original and the quantized values. In naive quantization, these errors accumulate and cause significant performance degradation. The brilliance of GPTQ is that it doesn't just accept these errors, it redistributes them to minimize their impact. Let's see how. The Hessian and the error redistribution. The secret sauce of GPTQ is the Hessian matrix. The Hessian captures how the model's error changes with respect to the weight changes, essentially a sensitivity map showing which weights are most important. The inverse of the Hessian tells us how to optimally distribute quantization errors across the weights. Specifically, we want to make larger adjustments to weights that have less impact on the model output. So wherever the impact is more, we want to change less, and wherever the impact is less, we have more freedom to change the weights. To make computations more efficient, GPTQ uses the Cholesky decomposition. This is a fundamental technique in linear algebra where a Hermitian positive definite matrix is like the Hessian that we are calculating is decomposed into the product of a lower triangular matrix L and its conjugate transpose. For a Hermitian positive definite matrix A, the Cholesky decomposition gives us A into L star, where L is the lower triangular matrix with positive diagonal entries. The Cholesky decomposition provides several benefits. It's approximately twice as efficient as LU decomposition for solving linear systems. It enables fast numerical solutions. It provides numerical stability for the GPTQ algorithm. So the Cholesky decomposition is a famous method to solve least square problems. So in our case, we compute the Cholesky decomposition of the Hessian inverse, which gives us an efficient way to redistribute the errors we talked about. So how the error redistribution works? When we quantize the weight, we create an error vector. We then apply the Cholesky decomposed Hessian inverse to this error vector to determine how to adjust the remaining weights to compensate for that error. This redistribution ensures that quantization errors have minimal impact on the model's outputs, preserving performance even with significantly reduced precision. So now coming to the algorithm steps, let's walk through the GPTQ algorithm step by step. First, we initialize our quantized weight matrix Q to zeros. We then initialize a matrix E to store quantization errors within each block. We pre-compute the Cholesky decomposition of the Hessian inverse for efficiency. Then we process the weight matrix in blocks of columns. For each column in the block, we quantize it and compute the quantization error. We use the Hessian inverse information to determine how to adjust the remaining weights in the block. After processing a block, we update all remaining weights in the matrix to compensate for the errors in that block. The block-wise processing is a key efficiency feature of GPTQ. We process weights from left to right with each block typically containing a small number of columns. As we quantize each column, we immediately update the remaining weights in the block and then update all weights to the right of the current block. This approach ensures that the most important weight interactions are handled properly while making the algorithm computationally efficient. So there are various benefits of the GPTQ algorithm. So it drastically reduces model size through 4-bit quantization, cutting memory requirements by up to 8x. It preserves model accuracy by intelligently redistributing errors. It uses Hessian information to respect the relative importance of different weights. It enables efficient inference on resource constrained devices. It requires minimal calibration data, just a few hundred examples. If the code makes more sense to you, here is the code regarding that. So I have in Colab, I have created a GPTQ class. So in the quantized layer weights method, we compute the scales and the zeros for the quantization. So we create a quantized output and an error matrix to store quantization errors within each block. We compute the Hessian matrix, which can be calculated like this. So process weights block by block. So for each block, we do the Cholesky decomposition for the Hessian block. So for each column in the block, we perform the quantization based on the current scale and the zero. We compute the quantization error for the column, and then we use the Hessian information to determine how to adjust the remaining weights in the block. We redistribute the error using the Hessian inverse, and then we utilize the Hessian inverse information to determine how to adjust the remaining weights in the block. So for this, for testing this, I created a simple model and then pass the MNIST dataset. I did not train it specifically, so this model is as such useless, but you can train the model and then try it. You can check the original GPTQ code in the repo as well. I'll give the link in the description below. Now let's try to benchmark Llama 3 using GPTQ. So for this in Colab, we install Accelerate, Optimum and Transformers. Then we install the GPTQ model. Before the recommended package was Auto GPTQ, but they are deprecating that package and recommending this one, this GPTQ model. So we'll try to do this. Production ready LLM compression quantization toolkit with inference support for both GPU CPU via Hugging Face, VLLM or SG line. So all these features are supported. All these models are also supported. Also downgrade the NumPy version to less than 2. The new NumPy version is unstable at some places and I was getting an error which this downgrading resolved. But let me know if you are able to make it work with NumPy 2 as well. So here I am loading the model Llama 3, but on Colab I was not able to quantize the model because of out of memory issues. So move to using an already quantized model that is there on Hugging Face. So from this guy Astronomer. So now when running through the benchmark code, this is taking around 6 GB of memory, and the time for running the 100 samples in a dataset is around 1 minute 40 seconds with perplexity of 5.69. As you can see, comparison with the previous quantized model of BitsandBytes, there is good improvement in terms of memory, but the time and perplexity is slightly worse, although quite comparable. This is probably because we are using the 8-bit model right now. So these are the metrics. So now let's talk about activation quantization or AWQ. It was published in June 1, 2023. Activation aware quantization doesn't quantize all the weights, but instead it preserves a small percentage of the weights that are important for LLM performance. This significantly reduces quantization loss such that you can run models in 4-bit precision without experiencing any performance degradation. So let's go over the theory a little bit. If W is the weight matrix and X is the inputs, then the output activations Y is going to be Y into WX. If QW is the dequantization weight matrix, then the goal is Y should be almost equals to QW into X. Now if we bring in a scaling parameter delta in terms of the absmax form given by the maximum of the absolute value of W and divide it by the total range supported by 8 bits. So your quantization dequantization becomes in this form: delta x round of w by delta. So now let's explore the error due to quantization. We can define it as the absolute error between the actual output and the output due to quantization. So we can replace the QW part with the formula that we had in the previous slide and divide the scale parameter delta to the actual weights. Thus we can take out the delta from both the values, take it outside, and also take out the inputs x from both the values and take it outside. Delta would be positive because if you see the formula for delta, there is the absolute function there as well. Also, generally x would also be positive because generally we will run them through the ReLU function, which also keeps only the positive values. If we take the middle value and call it round error of w by delta, then we can replace the part with round error function. We will use this later. If we assume each variable in w by delta is a uniform distribution, the absolute error will also form a uniform distribution in the range 0.5. So expectation of the round error of w by delta is 0.25, which is constant. In this case, the quantization absolute error of weight only quantization multiplication is proportional to the quantization scale delta and the input activation x. In a single group, delta is constant for everyone. So for a single group, this quantization error is proportional to x. In other words, we can say that the quantization error of weight only quantization is activation aware. If the input activation magnitude is small, the quantization error is small, and if the input activation magnitude is large, the quantization error is large. Therefore, if we could somehow reduce the input activation magnitude in weight only quantization, the quantization error can be reduced. So if we continue to the previous equations that we had discussed, y equals to wx, we want to reduce the magnitude of the activations in the input. We can inversely scale the activations, and then to counter that we will scale the weights as well, which is almost similar to quantizing the scale weights as seen in the equation. So now we can replace w by ws in almost all the equations. Finally, we can give the error equation in this manner. We have just replaced w by w into s. Also, if w by delta is a uniform distribution, then round error of ws by delta prime is also a uniform distribution, and the expectation of that will also be 0.25. So now we can do a comparison between error prime and error. We divide by both the forms. Because the expectation of the round error is the same, we cancel out the round error parts, and also x gets cancelled. So the remaining becomes delta prime by delta into 1 by s. We want to move towards lower error. That means error prime needs to be less than error. One way would be to go higher and higher s while keeping delta prime close to delta as per this equation. From this analysis, they set the objective as finding the best s, where loss is the least squares between the changing done due to scaling and quantization with the actual activations. Okay, now let's do a code walkthrough to understand the code. We'll go through the code in Casper Hansen Auto AWQ and the module Auto AWQ Quantizer. Now, based on the theory that we have discussed, if we go through the code, it would make sense. If you go through the quantize method, you will see step one is get the layer, extract linear modules, extract input features, and then we filter out the linear layers we don't want to exclude. Then we search for the best scale and apply the best scale. Next, we compute the clipping list and apply the clipping list. Finally, we quantize the weights. The quantizing the weights part is simple. If we know the scales and the zeros, we can apply these scales and zeros and perform the quantization. So point is how to search for the best scale. So for this we go to the search best scale method. So for this we start with the absmax of the weights. We compute the per channel mean of the input activation with chunking. Then we compute the output of the module, and we go to the computing the best scale, which is input, where we pass the input, the W mean and the X mean, along with the F16 output. So here we are performing the grid search here, where we take the X into inverse of S, and then performing the pseudo quantize of the Q into W into Q of W into S. Once done, we calculate the output and then compute the loss. Based on whichever is the best loss, we set the best scale based on wherever the loss is the minimum. So now let's go into the compute loss method. So here we are computing the loss based on the difference of the FP16 output and the in W output. We sum them up, normalize the loss by the total number of elements. So basically, as per the paper, we compute the loss, or rather we calculate the loss, and then we select the best scale based on the wherever the loss is the minimum. In the code, we first installed transformers and accelerate. Using the config as 0 point is true, Q group size is 128, W bit is 4, and version GM. You can now quantize the model, but this was taking 2 hours in Colab. The dataset that we are using is the pile dataset. Since this was taking a long time, I took a quantized model as done by Kasper Hansen in Hugging Face for Llama 3. It took around 5.69 GB of memory, and the time taken was 2 minutes 43 seconds for 100 samples of our data. So as compared to GPTQ, memory has improved, but the time has increased a little bit, and the perplexity has also improved compared to GPTQ. So now let's talk about GGUF. GGUF is a new format introduced by the Llama CPP team on August 2021-23. It's a replacement for GGUF. So GGUF is not a quantization technology, but specifically it is used for storing the model weights and running them on consumer hardware such as our laptop. So that is sort of the goal of GGUF. Right now, so there can be multiple quantization techniques used in GGUF. Some amount of quantization is also implemented on them, but they are basically linear quantization. There is a nice history about how GGUF came about is there in this WikiVoikis article, GGUF the long way. So this is sort of how the GGUF model weights are there. So the first 4 bits is the GGUF magic number. So the first 4 bits is the GGUF magic number. Then the next 4 bits is the GGUF version. The next 8 bits is the tensor count. The next 8 bits is the metadata of the KV count. Then we have the key value pairs, various metadata key value pairs, and then the rest of the files with the tensor values. So the quantization in GGUF is based on linear quantization. We have discussed this in the previous video, which you should take a look at. For linear quantization, we can take the quantization operation as the inverse scale of the weights W and a 0 point Z, and then we can do a rounding operation on that. So the dequantization process should remove the 0 point and multiply with the scale. Now this scale can be the min-max scalar. So we take the min-max of x and the min-max of the quantized range, because we want to fit the full range of x to the full range of quantization. So S is x max minus x min by q max minus q min, and hence Z will be q min minus x min by S. So the quant descriptions are mentioned in the Hugging Face documentation. For example, Q4K is super blocks with 8 blocks. Each block has 32 weights. So W is Q into block size of Q bit plus block size of 6 bit. block min of block scale of 6 bit plus block min of 6 bit. So how this is implemented can be seen in the code. We go through the llama cpp gguf quants.py. So there, if we see in the, for example, in the q41 class, we have the max is the max of in the block and minimum as the minimum of the block. So your denominator becomes a max minus mean by 15, which is the 2b minus 1. So assuming that b number of bytes is 4 here. So then, so you do each element in the block minus the minimum into or rather divided by the denominator value, and then you do the rounding function. So that is how you calculate the quantized value. Now to use the GGUF models, there is the Hugging Face class that converts GGUF to Hugging Face format, but the memory requirements for that is too high. To run llama cpp, I did a pip install llama cpp with the flag ggml CUDA on. Installing this took around 30 minutes. Then I can download the GGUF file from Hugging Face and load it using the llama class from llama cpp. But to calculate the perplexity, I have to build from source, because then I can use this llama perplexity command. Here we pass the model and the dataset file. So now running this. Once we run this, we can see that the memory requirement is 4467 MB. Time it took is 1.48 minutes. And the perplexity is 3.2154. Another popular method is using Ollama for local inference. I've made a video on using Ollama for local inference along with other methods for doing local inference. Comparing this with the previous methods, the GGUF model seems quite good. Interestingly, the perplexity is even better than the original model. But yeah, definitely the memory and the time requirements have also decreased. So now let's go over half quadratic quantization of large machine learning models. So this came out in November 2023, and this is the blog that they have shared. Here they have mentioned some points. Calibration data bias. The quality of calibration can be negatively affected depending on the calibration data provided. Calibration can be a heavy computational process, especially for very large models, which make it very difficult to test and deploy multiple models. So in this blog, they explored half quadratic quantization, which minimizes errors in the weights themselves, preserving the model's fundamental building blocks. This method uses a sparsity promoting loss function, where we take LP norm less than 1, that is that more accurately represents the distribution of outlier weights, which are often critical to model performance. They use mathematical decomposition to break the overall problem into simpler sub-problems and solve those sub-problems in a few steps. Instead of using gradient descent methods, they use closed form solutions for each step. Thus, they can do things faster, while gradient descent will take thousands of iterations. The quantization is done on the GPU with half precision and uses the CPU to transfer data once the solution is done. We are now going to go through the math and try to build the algorithm. There is not much explanation in the blog, and the equations are not very clear, as there are only couple of links. So I worked out a lot of the details myself. In case you find gaps in reasoning, please send me an email regarding this. So we can start with the definition of linear quantization. Here the notation is slightly different from what we used in AWQ. There the Q meant both quantization and dequantization, but here Q means quantization, which is you inverse scale the weights because you want them to vary between two ranges of similar size, and then we add a bias also called the 0 point. And Q inverse stands from the inverse of the quantization process, which is you remove the bias. 0 point and then multiply with the scale. So you get WQ here and you do the inverse quantization here. As we have discussed before, we are concerned about the quantization error, the difference between the weights and the quantization dequantization operation on the weights. If we define a function transformation on this error phi, which should be monotonic, then we can try to find the minimum of this function for some values of z and s. This will translate to argmin of w minus q inverse q of w. In the blog, they mentioned that you can consider phi to be LP norm as it's a sparsity promoting loss. Okay, but this is still hard because this phi is non-smooth. Here rounding, so Q involves discrete rounding operations. The composition makes it very non-convex. So this one is non-convex. So let's discuss about the penalty method. Let's consider a function f of x equals x to the power 4 minus 4x squared plus 3. Notice this function's complex landscape. It has two global minima as x plus as x equals plus minus square root of 2, where the function value is negative 1. There is also the local maximum at x equals 0, where f equals 3. This is a classic non-convex function. Multiple peaks and values create a challenging optimization landscape. An algorithm starting from the wrong place might find a local optimum instead of the global one. The key challenge: how do we ensure we find the true global minimum at negative 1 rather than getting stuck at the local maximum of 3? Now let's see what happens when we add constraints to this same function. Here is our same function, but now with the constraint x must be greater than or equal to 0. This red line marks our constraint boundary and the shaded region shows where solutions are allowed. Notice what happens. Our constraint eliminates the left side of the function entirely. The global minimum at x equals negative square root of 2 is now forbidden territory. We now have three key points. The gray dot shows our old constraint optimum, now infeasible. The yellow dot at x equals positive square root of 2 becomes our new constraint optimum with value negative 1. The orange dot at x equals 0 sits right on our constraint boundary with value 3. This demonstrates a fundamental principle that constraints don't just limit our choices, they completely change what optimal means. Our best achievable solution shifts from left to right. So how do we actually solve this constraint problem? Enters the penalty method. The penalty method transforms our constraint problem back into an unconstrained one by adding punishment for constraint violations. Here is our original function in blue. For our constraint x greater than or equal to 0, we add a penalty term mu times the square of max of 0 and negative x. This creates a penalty only when x becomes negative. What's the magic happen when we increase mu? With mu equals 1 in green, we see a gentle penalty pushing the minimum right forward from x equals negative 1.4. At mu equals 10 in orange, the penalty becomes stronger, shifting our minimum to around negative 0.3. Finally, as mu equals 100 in purple, the penalty creates a steep wall, forcing our minimum to nearly x equals 0. See these arrows? They show how increasing the penalty parameter progressively moves our solution from the unconstrained optimum towards the constraint boundary. As mu approaches infinity, we approach the true constraint solution. The penalty method brilliantly converts our constraint problem into a series of unconstrained problems that converge to the right solution. So now going back, let's say we call this W minus Q inverse Q of W as WE, and we write the overall optimization function in terms of the penalty function. Notice that there is no s here. The author said that they fixed the scaling parameter s to make the problem simpler and only optimize in terms of the 0 point z. Also, nice thing about writing it in this manner is you get two terms here. First term and this is the second term. And we can optimize them independently. Why this formulation works? Because when beta is large, this penalty forces WE almost equals to W minus Q inverse Q of W. When beta is infinite, we recover the original problem exactly. But for finite beta, we have a smoother problem we can solve iteratively. Now let's say U equals to WE. So and consider a function fu is p norm of u plus beta by 2 u minus x whole square. So x is actually the error term. Considering u greater than 0, f of u is u to the power p plus beta by 2 u minus x square. Since we want to find the minimum u, we take the derivative f dash u equals to p into u to the power p minus 1 plus beta u minus x, because with derivative that, and we equate this to 0. In derivative the 2 comes before, so 2 gets cancelled out. So we get this expression. Now we can do some rearrangement. U minus x equals to p by beta u to the power p minus 1, which means u equals to x minus p by beta u to the power p minus 1. Since beta is large and p is also some fraction, which means we can say p equals to 1 by something, we can absorb p in beta. So u equals to x minus 1 by beta u to the power p minus 1, and this is valid when u greater than 0, means that u is constrained to be greater than 0. Hence we can write this as max 0 x minus 1 by beta u to the power p minus 1. But since u is actually WE and WE is the error part, that means we can also replace with the current error term here. So this becomes max of 0 sine of x into mod of x by 1 by beta sine of x into mod of x to the power p minus 1. So u we are saying as sine of x mod of x. Since p less than 1, we can solve this equation iteratively, where we take the shrinking operator which shrinks x and 1 by beta. Here we are keeping u, and here we can take the sin x outside this equation. So it becomes sin of x max of 0 mod of x minus mod of x to the power p minus 1 by beta. So this is like keeping this part positive, so we can replace max of 0 and something as ReLU. That means that the next iteration of WE is when we apply this shrinking operator x beta, and this becomes this one, sin of x ReLU mod of x minus mod of x to the power p minus 1 by beta. So now we can see that the first part is reduced. What about the second part? The second part is dependent upon z. So we have to do something about it. Something about z. We take the second part here and mark it as the second term. Since beta is some number greater than 0, so taking an argument of that, we can ignore beta and also replace WE by WT plus 1, since we are now in the next step for WE and Z. So we replace WE by WE t plus 1, which we have calculated. The new quantized weights, or the new quantized weights, that is WQ t plus 1, is rounding of W by S plus Z of the previous time step, and then we round the function. So the inverse quantization would be we scale wt plus 1 with s and remove the 0 point. So we replace this in the term 2 equation. We get T2 equals to argmin WET plus 1 norm of WT plus 1 minus W minus S into WQ T plus 1 minus Z. Now we do some rearrangement in this term 2 equation. We expand the brackets and take out all the terms. So this becomes WET plus 1 minus W plus S of WQ T plus 1 minus Z, bringing minus Z to the front plus SWQ. So this one comes here, SWQ T plus 1 minus Z WET plus 1. So this is some rearrangement. Since we are taking root over of the square of the values in this L2 norm, we can invert all the signs. This means that the minus becomes plus, plus becomes minus, minus becomes plus, plus becomes minus. So now we can take the brackets. We take out the Z S here. This S we take it out. So it becomes Z minus S into WQT plus 1 minus W minus WET plus 1 divided by S. Now we have this equation, right? We have this equation. This has the form minimum, finding the minimum Z minus A to norm of Z minus A. So hence the solution is Z equals to A. So hence minimum of the T2 term means that for the next iteration of Z, we will say WQT plus 1 minus W minus WET plus 1 divided by S. You might ask, where did the S at the start go? The answer is I don't know. If the authors are watching this or anyone knows about it, please let me know. Now since the quantization is done in a block or similar group, this means Z is shared across the group. Solution becomes the mean over the relevant data set. This last part means that we are taking the mean. Now having built all this, we can talk about the final algorithm. For a specific beta, first we find the next WE, which is sine of x into ReLU mod of x minus mod of x to the power p minus 1 divided by beta, where x is the error term. Next, Z becomes mean of WQT plus 1 minus W minus WET plus 1 divided by S. And then we increase beta by some constant kappa, so that beta keeps on increasing in each iteration. So same is shown in the official implementation of HQQ as well. So GitHub Mobius ML HQQ code optimize. I'll share the link in the description. Each iteration we compute the quantized weights and the dequantized weights for the best k length 0 found in the last iteration. So we find WE based on the shrinking operator, and then we find the 0, which is the mean of WQ minus WF minus WE into scale as per the formula, and then we increment beta with kappa. In the shrinking operator function, they implement the formula where they take the sign and the functional ReLU. So this is implemented in this way, not in the main function, but in taking the absolute and taking the power and the sub, or rather in more lower level functions. So if the error is not improving, it means that we have found the minimum, and then we come out of the loop. To use HQQ in code, you can do pip install HQQ, and then you can use this HWQ config and use this in transformers for the various quantization levels. In my experiments, HQQ is slightly higher than AWQ. And if you remember, AWQ was activation quantization, while HQQ is only weights. You might be disheartened to see that after so much high level maths the results are quite poor, but don't discount HQQ so fast. The algorithm is really quite fast. It It is probably the only one that I could complete in Colab. For the other models, I had to download already quantized models. So in a way, this is quite good. Maybe in your case, you might actually get good results. So try it out and let us know in the comments. Till now, we have been talking about 8-bit and 4-bit quantization techniques. Currently, 4-bit quantization with some amount of QLoRa training is the industry standard. The next frontier in this field is somewhere between 1-bit and 2-bit LLMs. The most famous of these models is the BitNet by Microsoft. A lot of things have been done with regards to BitNet. So here you can see 17 October they came with the paper BitNet scaling 1-bit transformers for large language models. This was about going full 1-bit, that is having weights as 0 and 1. That did not work out that well. In 27 Feb, they released 1.58-bit paper where they went with ternary operators. Ternary operations are only for the linear parts. The activations were in 8 bits. In 21st October, they spoke about BitNet CPP, how to do packing and unpacking, and the TL1 and TL2 kernels. 8 November, they released BitNet A4 Activation 4.8 paper, where they added activations in 4-bit and some other modifications. 18 Feb, BitNet CPP paper is about the LUT operations or LUT implementations in BitNet CPP. Later, they also released the GPU versions and some trained models. So overall, in the industry, to make LLMs faster, we have moved from FP16 to Int4, and now we are trying to move to ternary operations. In the first paper, actually, they tried with the 1-bit system, but there was performance drop and the network was not able to learn effectively. So based on existing literature, they added 0 to -11 to come up with ternary numbers. Let's understand why ternary operations is also called 1.58 bits. Because think of what does 1 bit mean. It means you have two possibilities in your representation. 2 bit means you have 4 values. 10 bit means you have 2 to the power 10 values. So if you have 3 values, that means 1 bit is not enough, while 2 bits is too much. Keep this point in mind. We will explore this point later. In traditional matrix multiplication, you have many floating point operations. But notice that in this new system, if you have the numbers +1, 0 and -1, that means selecting the value if it's +1, not selecting the value if it's 0, and penalizing the value if it's -1. This results in 16 times faster operations. So assuming you have the weights W, we need to convert the weights to -1, 0 and 1. So the quantization function becomes Q of W is alpha into round clip W by alpha plus epsilon, and you are round clipping to -1 and 1, where alpha is the mean of the absolute values in W. This means first you take the original weights, then you calculate alpha, which is the mean of the absolute values in the weights. Then you normalize with this alpha and a small epsilon, so that there is no divide by 0 error. You clip the result to -1, 1. So for example, 1.71 is taken as +1, minus 0.73 as -1, 0.24 as 0, minus 2.20 as -1, and 0.12 as 0. Final result is 1, -1, 0, -1 and 0, with alpha as 0.41. Similar to weight quantization, activation quantization is done to 8 or 4 bits. There the formulas are similar to the AppsMax quantization that we discussed before. Quantization values of x in int8 is int8 quantization of x is gamma divided by 127, which is the range, into round clip of 127 into x by gamma plus epsilon, and you are round clipping to -128 and 127, where gamma is the maximum of the absolute values of x. In case of 4-bit, it's the same formula, just that you have, instead of gamma you have beta, and in the denominator you are saying root of 7. There you are doing round clip between -8 and 7. You are doing 7 into, or rather root 7 divided by beta plus epsilon into x. where beta is the mean of the absolute values of x. So the difference there is that gamma is the max and beta is the mean here. Steps for both are similar. So we have the original activations in higher precision. We find gamma, which is the max absolute value. We scale the max value to 120 minus 128 and 127. We round clip to the nearest 120 in 4 values. So now we'll do the bit linear replacement. In the transformers architecture, there are two high level blocks. Input goes through a multi-head attention part, and the output of the multi-head attention goes through a feed-forward network part to get to the final output. If we expand the multi-head part, there the same input is fed to 3 blocks: query, key and values. The output QKV of these 3 layers is fed to the attention block with edge heads. Then these edge outputs of the attention block is concatenated and passed through an output projection block to get the final output. We replace the query key value and output block with a bitlinear block. Now we go back to the transformer architecture and expand the feed forward network part. Feed forward has 3 blocks. The same input goes to an up block and gate block, and then the outputs for the up block and gate block are combined, and then they pass through the down block. We replace all these 3 blocks with bitlinear operation. For the activation quantization, let's go back to our overall transformer architecture, which has the multi-head attention part and the feed forward network part. Expanding the multi-head attention, we have RMS norm, which goes to 4-bit quantization, and after that we have query, key and V matrices. Remember, we just discussed the weights were in 1 bit, but the activations will be in 4 bit. Then attention calculation is done. After that, another RMS norm is there. We perform top case pacification, and then we do 8-bit quantization, and then we multiply with the out projection. In the paper, they did 50% top case pacification for the attention scores. This strategy, along with hybrid quantization, is done to reduce the errors due to outlier channels of the activations. Now let's go over the FFN breakdown. The input to the FFN is the activations from the multi-head attention part. The RMS norm stabilizes the activations before quantization. These are then passed through 4-bit quantization. They are passed in parallel with up projection and gate projection. The up projection expands to a hidden dimension. The gate projection creates gating values for control of information flow. The output of the gate projection is passed through a ReLU square function, which provides aggressive spacification than normal ReLU. Then we do element-wise multiplication of up and gate results. Then there is a second RMS norm before final activation. Then we have 8-bit quantization for output activations. Then a down projection reduces the dimension back to model size. Then a final FFN output ready for the next layer. This is the overall flow of activations. Finally, I want to show how bit packing and calculations are done for the ternary bits. BitNets use ternary values -1, 0 and 1. Most architectures have instructions and other information in bytes, which is in 8-bit. To be able to store the ternary weights, we can do packing. Packing is a technique used to combine smaller pieces of information to form a complete byte. For example, if you have information that can be expressed in 2 bits, you can either use a single byte inefficiently, that is leaving 6 bits unused, or combine 4 2-bit units in a single byte for maximum efficiency. This packed byte can later be unpacked to access individual pieces of information. But can we do even better with ternary weights? In the paper, they implemented 2 methods. One is the TL2, which is simple packing. TL2 uses the straightforward approach. Each ternary value uses exactly 2 bits. So we fit 4 values per byte. For example, let's say we have the numbers -1, 0, 1 and -1. These can be represented in 2 bits, something like 0, 1 and 2, and then the corresponding binary value can be filled in 76, 54, 32 and 10. So value 1 can go to 76, value 2 can go to 54, value 3 can go to 32 and value 4 can go to 10. This uses all 8 bits efficiently and is simple to implement. Another packing strategy is the TL1 approach, which does 1.625 bits per wait. TL1 uses a more sophisticated approach. The key insight is that 3 to the power of 5 equals 243, which is slightly less than 256. What is 2 to the power of 8? This means that, let's say we could have a 5-bit number. Now we can fit 5 ternary values in almost any 8-bit combination. We have 13 unused numbers, giving us 94% efficiency at 1.625 bits per wait. This is the TL1 representation. We are using all the 8 bits, just that possible values are 256 in 8 bits, but we are only limiting the possible values to be between 0 and 242. And each value will represent some number in the ternary space. This means that values 243 to 255 remain unused, and we have 94.9 efficiency. Now, because we have changed the representation when doing bit packing, the calculation complicates because for each number we have to unpack and then perform the matrix multiplication. For example, let's say we have 4 activations X, Y, Z and M, and weights are A, B, C, D. We can perform the calculations as is. This is the multiply add method called the MAD method. Is there a way to perform the sum X into A plus Y into B plus Z into C plus M into D faster? For this solution, we can leverage the power of lookup tables. We can use element-wise lookup table where given 2 activation values, we can consider 2 values for ternary. 2 bits for ternary has 9 values or 9 combinations. So we'll pre-compute the output for these 9 values. During calculation, let's assume that the weights are +1, -1. Then it finds the matching row in the LUT table and directly takes the result. Thus, actually, no multiplication step is required, just addition of the results, and since they are taken in chunks of 2, number of additions also become half. So we process the pairs of values and then combine the results. In summary, both TL2 and TL1 transform how we store neural network weights. TL2 offers simplicity with 2 bits per wait, while TL1 achieves maximum compression at 1.625 bits per wait. With current hardware, this is how much we can do these bit operations efficiently. Of course, there is the possibility that if we can build a hardware that can save ternary bits directly, we will have even greater efficiency. Now to run BitNet, we need to do some LLVM installs and then install BitNet from scratch. BitNet CPP code is forked from Llama CPP. Hence, running process is quite similar to GGUF as we have seen earlier. And we can also calculate the perplexity in similar manner using the same perplexity command. But the perplexity that we are seeing is quite low. Then you might ask, why did we go so in depth into this topic if this is not that usable as compared to other algorithms that we have discussed till now? I believe we are almost there with BitNet and things will be comparable soon. Anyways, thanks for watching this long video. I provide one-on-one mentoring on TopMate, so if you're interested, please book a meeting there. Thanks for watching.